Caleb.
I'm Devin.
And I'm Blaze. And this is the Reflector dish imaging system. So this is our design. So it's we have three primary components. We have our small mount for our smaller feed rings, our large mount for our larger feed rings, and then our primary scanner housing. It's on the front of it are these two LED lights. These are status indicators. On the bottom here is our distance sensor and a laser pointer to show what section of the dish is pointing to. And this is housing all of our electronics. So how the system works. The system takes measurements of spherical coordinates and converts them to Cartesian coordinates. Our Arduino takes in the angular measurements from our two 180-degree servos, as well as the radio distance measurements from our time of flight sensor. Once it acquires those, it puts them into an Excel spreadsheet. On completion of the scan, that data is taken and put into MATLAB, and we have it to develop our 3D models. So why are we doing this? This device right here, this is the Army's Joint Threat Defender system. It's a training aid used for air crews. It simulates ground threats. Crucial to the system's functions are its two 8-foot reflector dishes here and here. If they're damaged, they will lose functionality and the system will fail eventually. Currently, Tobyhanna Army Depot does not have a way to specifically identify damage on the dish, but they can identify a dish. So their current method to repair these systems is to entirely replace one of those 8-foot dishes. They're about $320,000 each. So what Tobyhanna needs is a device that can find the faults on this dish and repair the surface essentially. And so the requirements of Tobyhanna. This device needs to identify the size, location, and type of deformation that can be found in one of these dishes. This includes things that are about diamond size to the entire dish being formed. The design should be able to produce a viewable three-dimensional map displaying the detected deformations. This device should be compatible with the Joint Threat Defender systems, being that it fits in the feed rings that when they're under maintenance you can have access to those. And the system should also be portable and easily switchable between different dishes.
So under our project management, above you can see our schedule. We started ordering parts before we even gave our initial presentation in the fall. And this allowed us to come back to campus and start assembly and start getting ready to go test and experiment with our product. Our coding was done continuously, running alongside the assembly and testing, just so we could work out any bugs and optimize the system as needed. The first testing date was February 20th. We had our first prototype up and ready to go. We went down to Tobyhanna Army Depot, and that was the first time we tested it on base. Our first revision started pretty much the day we came home from there, so the 20th, all the way through when we did our next testing, which we went back to base on the 21st of March. And final revisions began a little bit before that because we noticed some of our components were not acting the way that we wanted them to. So the 15th of March is when we started that, all the way through right before this presentation. And our final testing day was the 11th of April, where we went up, we tested the system, we got a great scan, and we've been doing final debugging and troubleshooting up until this point today. Above you'll see our breakdown structure. Not much has changed from last semester, except for a couple of components, such as the servos have been switched in for the stepper motors. The drivers are now out of our system because we went to the servo motors. The buck converter's back in, yet again, for the servo motors. More on that later. Here's our budget that we actually used. Overall, it totaled to about $337 because we had to replace components and get some new components in other areas. So even though it increased from last semester, it's still well under the $500 limit we had. And here's our calculated real-world budget, accounting for labor costs, licensing for programs we use, and machining costs, which total to around $12,617. And for our ethics and standards we follow, these also remain largely unchanged from last semester. There's no real malicious effects of our product, so it fulfills the code of ethics. The system is well under 50 pounds, it's about 3 pounds of weight, so definitely and portable. The lasers aren't emitting too much dangerous radiation, and they're well within the 300 to 4,000 nanometer wavelength by 60825-1. Definitely costed less than $500 and was completed within 2 semesters.
So indoor mechanical specifications, they're the same from the fall semester. Our device has main housing, our quick detach system, and then our two mounting units, to mention a few pieces. And most of it's machined and 3D printed.
The electrical specifications are almost the same. The only difference is we switched out stepper motors for servos.
Our software specifications are also the same, besides switching from controlling the steppers to controlling servos.
So into our mechanical upgrades. Since the fall semester, we've done testing and we've come to the conclusion on a multitude of parts that they need redesigning and resizing. So the two mounting units, namely, they have been simplified significantly. They are now single pieces that minimize the number of pieces. They require a minimum amount of supports while printing, as well as the sprung pressure pads that we initially used. They've been removed. In our main housing, due to the fact that we switched to servos, we had to redesign the top and bottom to house those. In addition, our side sections, our mid-sections there, they were resized to fit some of the more internal components that we couldn't account for in the fall.
As for our electrical and software upgrades, we've moved from Excel graphing to MATLAB graphing. This is because Excel only allows you to graph 250,000 data points, and we were at the range of 1.5 million data points, and that was on this wooden elliptical dish that is a 17.5-inch long diameter by 16-inch short diameter, and that was on a data scan. This caused us to have to move to something that didn't require a Z extrapolation matrix that was pre-done, which MATLAB does not require, so it can do all the graphing itself. The stepper motors were replaced by servo motors due to the fact that our stepper motor drivers were not able to actually deal with the pressure we were putting them under to do what we needed to do, and servo motors were just easier to control and easier to get data out from. We also switched to continuously sending data from the Arduino to Excel through a wired cable because using any sort of array in the Arduino severely limited the amount of data points we could take, so we removed that and sent the data continuously to Excel. These are our Arduino commands, the first one being the run on system. This actually controls the system's running. This takes our measurement data from our time of flight sensors and our servos and sends it to Excel for final mapping later on. Our calibrate function finds the edges of the dish and then sets that as an edge condition. It also calibrates offset so that the system isn't perfectly level. It can still find essentially what is straight down onto the center of the dish. The serial event function is listening for a button press in Excel, and then will tell the system to either run the run system function or the find on dish function, depending on a couple of variables. The set VL53LOXID just initializes our time of flight sensor, and the find on dish function takes user imported data and will point to a specific area on the dish where that data point is from. This is our Excel data collection. This is what you will see when you look at the data as it comes in. The data comes in from the Arduino to Excel, and the first block that says time just tells you the timestamp when the data was taken. The channel labeled channel 1, it just displays the word start. Channel 2 takes your distance measurement. Channel 3 is your feet angle from the top servo, and your channel 4 is the theta from the bottom servo, and that on the left here is just a pretty version of our data after we filtered it and looked through it a little bit.
After the data is collected by the system, the user imports the Excel data from the previous slide into MATLAB using this user interface. The offset field there was given during system calibration. The smoothing iterations changes how smooth the mesh is when it's generated, and the z-axis limits are set by the user that can change the graph. The user can choose to filter the system data, or they can choose to include all the data points. They can choose to show a point cloud or all the coordinates of the system, which will generate 2 additional graphs. And the interpolation method just changes the equation used to fit all the data points. Here's the 3D graphing. So on the left, you'll see the smooth mesh. This is the default graph that's always generated, and it creates a smooth surface of the object that you're scanning. On the top, you'll see a show all the coordinates graph, and this actually shows like every single XYZ coordinate, which are those blue dots. The user can click any of those points, and it'll tell them the XYZ coordinate for that point. And below that is a point cloud, which gets rid of the rough mesh from the top graph and will only display the points.
So these are our Excel commands out page. When you're sending stuff to the Arduino to actually run it, this is what you see. Channel 1 changes between true and false, being controlled by the button you see there that currently is displaying running. This is displayed when channel 1 is outputting true. It'll display standby when channel 1 is outputting false. Channels 2, 3, 4, and 5 were mostly defined on dish. Channel 2 will cause the system to cause the find on dish function. Channels 3, 4, and 5 are the user inputted variables, with channel 3 being the X value, channel 4 being the Y value, and channel 5 being the Z value. So we went up to Toby Hanna 3 different times this semester, for 3 different days for 3 different testings. On the 20th of February, we went up and we actually took the feed mount and the waveguides out of the JTE and put our system in to test the mounting of it. And we found that our mount was too small, so we had to go back and redesign the mount to get it actually really fit. On the 21st, we went up with a mixed design. We still had step motors in the top section to control the actual movement around the top, and there was a servo in the bottom for our theta value. While we were up there, the stepper motor died. We got our first data points though that were useful, so we actually could start looking at the mapping of the dish. This is also when we decided to go fully to servos because the top stepper motor died. On the 11th, we went up with our final design. We got a full scan of the dish. We took physical measurements to check between what we measured and what the dish's actual shape would be. This is the testing we did on campus. This is where we tested all of our code and anything that was going wrong. As you can see, there was a lot of things that went wrong, as the video is showing the reason we got rid of steppers and went to servos, because this would happen randomly with no way to predict when it was going to happen. We tested on the wooden bowl that you see in the front. This is where all of our code was tried. We tested to try to find dents, and any of our functions were all tested on that bowl.
So our test results from Toby Hanna, we were able to generate 3D graphs of the antenna, of the JTE antenna, which can be seen on the left there, the smooth mesh and the show importance graph you've seen there. We found while testing that data points are within plus or minus 3% within each other, which was more precise than would be expected. And we also had strain error where the bottom servo, when it went past 133 degrees, the distance sensor would stop recording data, which caused a small area of the dish to not be scanned. And you can see that actually in the graph. It looks like a chunk was taken out there. We could not replicate that on campus, so we don't really know what happened there. We also took physical measurements of the antenna, and we compared those with what our system was recording. So the actual radius of the dish is 4 feet, or that's what we measured there, and the depth of the dish is 1.26 feet. And our system recorded measurements can be seen there also. Using that data, we calculated the parabola of the dish, which is just a measure of its curviness, and we were within 2.8% of the curviness of the dish parabola. And in our campus testing results, we attempted to simulate dents by placing objects in a wooden bowl, which can be seen in the two pictures, and we created 3D graphs. As you can see, they look pretty distorted. We have quite a few outliers in the data, and we could not reliably show dents on the surface. We pick up things that we thought maybe were these dents or these objects we placed in the bowl, and other times it wouldn't be picked up at all. And our scan time was 1 hour and 17 minutes with the final iteration of our code. Some areas of improvement, so better components, a more accurate distance sensor to actually pick up small dents, and servos that can do smaller angles so you can cover more of the dish's surface would help a lot. Improving automation, so creating a top-level user interface that combines Excel and MATLAB so you don't have to open both. And also combining the calibration and scan functions, so that's all in one step. Highlighting dents to the user and automatically sending that back to the Arduino to find on the dish would improve our system greatly. And finally, making it wireless so that it's much easier for your setup and you don't need an outlet to run the system when it's out in the field somewhere. Would help greatly also. So in summary, we meet all of the requirements that we needed. We were able to hit 3 of the 4 requirements. So our system is portable and it fits the JTE antenna, and it's able to create 3D graphs of the surface of the antenna. However, we cannot reliably show dents in the surface, so we did not get that requirement until we had needed.
For our acknowledgements, we would like to quickly acknowledge from Tobiana, Mr. James Jarrett and Trubowski for working with us on this product. They gave us the idea and they helped us hand in hand test it and work with it on base. And as far as Wilk staff goes, we'd like to thank our advisor, Dr. Sabuni. We would like to thank Dr. Zhu for helping us with some of our components, Dr. B, and we would like to thank Mr. Mitchell Adams for helping us also with some of our components.
When you started with the steppers, I suppose you were using counting steps to determine the angles, and you calibrate that against where a stop is.
Yes.
But now that you've converted to servos, you need a sensor to tell you where the thing is pointing. Do those servos have a sensor, an angular sensor built into it?
Yes.
And if they do, what's the resolution of that sensor?
So-
And what kind of sensor is it?
I'm not sure what kind of sensor it is. These are just basics parallax servos. They have the automatic feedback to go right back to the computer. They have angle measurements with
But
them.
what is the sensor? Is it a potentiometer?
It's an isolated rotary encoder.
Coaxially mounted or what?
It's an internal rotary encoder. It has a plus or minus 1 degree resolution currently.
Okay, so it's a digital encoder, is that right?
To my knowledge, I don't know the exact, but I believe it's somewhere in that realm.
Yeah. You need to understand what you've got. And if you're having accuracy issues, that may be where they're coming, some of those are coming from.
The accuracy issues are largely coming from the time of flight sensor. For the most, that's where the biggest accuracy issue is.
I'm sorry,
The time of flight sensor is where the most accuracy
time
is.
of flight was the problem
Yeah.
with the accuracy?
Yeah.
And then the resolution was coming from the degree iteration, or the degree resolution we had in the servos.
Yeah.
So from scaling from that solid bull there to an 8-foot dish, we would need finer resolution on that encoder.
So how many bits does the encoder give you?
I don't know how many bits it gives you, but what it gives out is it gives out the position of, you can control the angle of the servo's position. So if you tell it to go 2 degrees, it'll go 2 degrees from where it is. So you can give it from angles from 0 to 180 degrees in integer values.
Ultimately, it has to use a feedback loop
Yeah, it's
to position it.
yes, that was,
So ultimately, your accuracy depends on
yeah,
the data that comes
Yes.
off of that optical shaft indicator. And so if you're talking about one degree, it's probably 9 bits, giving you 512,
yeah.
1 part in 512 or something like that. So,
The Arduino library that I used has the basic positioning sensor for it is integer, so you can only move in 1 degree steps. You can mess with the pulse width modulation of the servos, which I didn't know you could do until much later as I was researching how to do things better. That you can actually mess with the pulse width modulation, and that can make for finer servo control. I didn't get a chance to try that. Our system pretty much stopped. Our time of flight sensor stopped being able to initialize. We had already burnt out. We had 3. We burnt 1 out pretty early on. This one stopped working kind of randomly for
are you
reasons like
talking the motors?
no, the time of flight sensors. We had 3 sensors. I burnt 1 out. I couldn't replace. If the system can't initialize the time of flight sensor, the system won't run because I can't get an angle. I can't get a distance measurement. So I mean, there's no point at that point. Our first one burnt up. The second one refused to initialize, and our third one had all kinds of damage on the actual sensor plating of it. So by the end of the beginning of this week, I couldn't do any more testing. So when I found the actual the finer controls for the servos, I couldn't test anymore because we couldn't get a part in time to actually test it on.
So your biggest problem is the time of flight sensor?
Yeah, the biggest problem is the time of flight sensor.
Okay, thank you.
So that's the most important question. So what's the required resolution? What's the target resolution? Like to be able to identify all the bugs, all the flaws in the system.
No.
So they wanted to be able to see dents that you can't see with your eye, or you can't like, if you.
So is there a number there? I mean, that's what
Yes,
they're shooting.
so roughly a dime, something about the size of a dime on an 8-foot dish. It's pretty much, like, the deformation is very small, it's almost invisible.
So you mean like into the diameter, right? Like,
Yes.
or depth,
That's-
has something to do with depth as well as the diameter?
Roughly as deep as a tenth of an inch to an eighth inch in diameter.
What did you achieve?
We couldn't get anything.
Like, were you able to identify anything?
No.
Why is
Not
that?
reliably. So what we tried to do was we would point the distance sensor right at the object we placed on the pole, and it would report a distance, and then we would point it a little bit off, right, pointing at the pole, so you should see a difference in the distance.
If you think about that, if I were to approach this project, that would be the first thing. Before you do any of the motion, you do a first test and see if you can identify just the center, identify bend. I'm not even moving, just do a basic testing. Is there bend? Are you able to identify that bend? You see what I mean? Before you go out the whole fiasco of the motion thing, you see what I mean?
The issue lies in the fact that we have to build a point cloud mesh out of various coordinates. So the finer resolution that we have, the finer dimensions we can put on that dip, or on that deformation. So it would require the entire system to get an angle here, or as we move along, it would build a linear or like a graphical positioning of that deformation.
I know, like I said, the first thing you should do is, are you able to identify a bend? Like, what's the resolution? How deep that bend has to be for you to be able to identify? I mean, if you don't do that, then you are just like, again, traveling without knowing where you're going. Because if you couldn't resolve that, the whole other parts of the system is pointless. Does that make sense? I mean, it's logical perspective, right?
Yeah. The Toyota sensor said it had an accuracy of 0.1%, or I think it was on 1 mil, yeah. And we figured that would be good enough. We'd be able to actually pick up like millimeter size differences in the ditch. And it proved to be not the case.
Yeah, absolutely. Because that's like a first validity testing. So when you go there, I mean, how deep the bend has to be, how deep it has to be for me to be able to have even a chance. If you couldn't, address that, you have to tell your boss, we better find a different way to do this, right? You better not get onto this road.
Also, the problem lies in the fact between the quality and cost gap. To jump to an improved sensor that can pick up even finer deformations or at an even finer resolution, it would be way overloaded at that point. It's a cost stacking issue.
Especially adding on to it more precise servos like we discussed earlier.
It boils down to that, like, it's a sensor, your laser you're using. You see what I mean? You get a laser, that's the first thing you should test is how I can use this laser to detect the bend. Just to put the bend there, see how sensitive that is. Because that's the foundation of this entire approach. If you couldn't do that test, the whole effort is when our motion system is meaningless, pretty much. Does that make sense, right? Okay, that's just how I see this project. Because, again, I keep, even when I was teaching you guys, I always ask you, you need to solve a simple problem first, because that's a simple problem. It's not moving, that's a simple problem. Otherwise, you see what I mean? You skip that, you jump right to skip the entire system as a whole, and that's what you get at the end, which doesn't make sense. You see what I mean? But overall, don't get me wrong, it's actually very good. I was going to ask the first question is how happy the customer is, because anytime you're dealing with customer, that's always kind of the bottom line, right? How happy was the customer?
They were impressed with what we were able to get, right?
Yeah, because you guys achieved a lot, don't get me wrong, but I wish just, if you answer that question, then your outcome will be much better. Because you get through the whole, actually, you have all the different components coming together. Don't get me wrong, it sounds like I'm criticizing you a lot, but it's actually, I'm quite impressed with what you guys accomplished. Especially, one thing you took more careful look at that first.
One thing I'd like to add, there are similar systems on the market, not specifically for our application, but they use them for ground plotting, for architectural purposes, or like at my job, we use it for site planning, for state. Those systems start well into the 2000s to 10,000 range, and they have their own built-in equipment as well, or software to accompany it.
In my opinion, you guys, the main mistake you guys made was choosing a laser. You didn't find the right one you needed to get for the job you are. did all the other good work, but you see what I mean? When the rubber hits the road, that rubber is not what you need.
The biggest issue with that was the massive cost jump from what we used. So even the one we showed in the improvement slide, that one was $50 some odd and a whole lot bigger.
Because you did all the good things, but at the end it kind of ruined it. All your effort is ruined by that one major thing. So I mean, everything else was fine. And everything else is really logical, and all the work that we're doing is actually very good work. You know, with the map, the mapping here, it's just not up to resolution. You see what I mean? Because if you want to address the resolution, you must get back to that sensor at the bottom of that, right?